So if you look at the last, the blue line there, so the blue is given by this one, okay? And then the red is given by this one, and then the green is giving you this one here, and the light blue is giving you this one, okay? Given by this one. So when you bond carbon with hydrogen or silicon with hydrogen, germanium with hydrogen, and the tin with hydrogen, these are all like carbon with hydrogens like that. And these are all non-polar. And this is symmetrical, so polarity cancels out. So the blue one there is non-polar. Everything is non-polar. So there's no dipole-dipole. They only interact through London dispersion force, right? Or weak dispersion force. Make sense? Yeah, only the weak dispersion force. But do you understand? Have you learned the fact that weak dispersion force increases as the mass increases? So as the mass increases, weak dispersion force increases also. So do you see how the boiling point of the methane, their CH4, is like negative 160, right? But then when you move on to silicon, it's a little bit heavier, right? Because carbon is like mass number is like 12, but silicon is um, like 28 or something, you know? So it's getting heavier as you go down, right? So as you go down, it's getting heavier. So that's why the boiling, that's why the, so as you go down, the mass increases. So therefore the weak dispersion force increases, and therefore the boiling point increases, right? So that's what this blue line is showing. Make sense? Now let's move on to the green line there. So you've got nitrogen with hydrogen, so NH3, and then the PH3, and then the ASH3, yep. NH3, PH3, and then ASH3 and the SPH3, right? So these are all polar. This is a non-polar. This one is polar. This one's polar as well. This one's polar too. So these are all polar, so that's why they are slightly above. The boiling point is slightly above, right? But they also have London dispersion forces in them. So they not only have this dipole-dipole interaction, but between every molecule there is also weak dispersion force, right? So that also the green line also exhibits this increasing boiling point trend, right? So why does the boiling point increase as you go up, as you move down? Because it's getting heavier, right? And with all of this is showing you that as the mass increases, the boiling point increases because the weak dispersion force is increasing. Okay? Except the 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 light blue and the red and green, they not only have the weak dispersion forces, but they also have the dipole-dipole because they're polar. Okay? So let me draw this again. Yeah, trigonal pyramid, that's right. So all of this, the blue one over here is tetrahedral shape because it's got four things attached, right? For example, carbon with hydrogen, 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 right? The red one here is linear. The green one there is pyramid. The light blue one over here is bent. Anyway, this is not the main topic, main concept. The blue one over here is only uh, weak dispersion force. All of this, they not only have the weak dispersion force, they also have dipole-dipole because it's polar. right? Now, all of this is exhibiting the trend, which is as the mass increases, the weak dispersion force increases, and therefore the boiling point increases. Okay? So this upward trend is not explained by the dipole-dipole, it's only explained by the weak dispersion force because mass is increasing. But what defies this trend is this group over here. These are the lightest, aren't they? They're with the oxygen, fluorine, nitrogen. Oxygen, fluorine, nitrogen is right here on the top. They're the lightest from their group. Yet they have got the highest boiling point. That's right. There's something more than dipole-dipole going on. So all these guys all have dipole-dipole. These guys all have dipole-dipole, you know? But it's got this special intermolecular force, which is what? The hydrogen bonding. These ones have, you know, you've got water molecule like hydrogen, oxygen, and this is slightly negative, right? And there's another hydrogen is slightly positive, and this is attracted there. And this attraction, it looks, you know, if it's slightly negative and slightly positive, and if there's attraction, we just call it dipole-dipole, right? But if this slightly negative guy is oxygen and this slightly positive guy is hydrogen, this must be classified as, although this is still attraction between negative and positive, we need to classify it as a different kind of bonding. Why? Because it's so much more stronger. See that? Yeah, it defies this trend. So it's the lightest, but it must have the highest. It's got really high. It's got hydrogen bonding, which has got very high, strong intermolecular force, and therefore the boiling point is like the highest from its group. You can see that the red one here is the highest among its group, and the ammonia are there is slightly below this SpH3, but is still higher than this one and this one, right? So hydrogen bonding is nothing more than what? A special category of dipole-dipole. So when oxygen is attracted to hydrogen, or nitrogen is attracted to hydrogen, or fluorine is attracted to hydrogen, then this must be classified as hydrogen bonding. You understand this diagram fully now? Yeah? Okay.